Welcome TCS members and friends to our TCS IBS seminar. Today we have a pleasure of hosting Professor Leonid Gorelik from Chalmers University of Technology from Göteborg in Sweden. And this seminar is a part of the activities of the Advanced Study Group on Coherent Charges, Spins, and Phonons in Superconducting Weak Links, which is convened by Professor Robert Schechter, who will now introduce our speaker. Please.
Thank you very much. It's my pleasure to introduce Leonid Gorelik, for many years member of our group here. Leonid Gorelik get his education in Moscow Physical Technical Institute. It's one of the best places for physical education in former Soviet Union. And right after finishing this institute, he moved to Kharkov and become a member of Institute of Low Temperature Physics, where I was used to work also. This is the place where I met for the first time Leonid Gorelik. So his scientific interests are more or less the same during whole years in his scientific activity, and it is low temperature properties of metals with emphasis to electronics behavior. And both theses which Leonid defended during these years, it's a postdoctoral thesis and habilitation degree, both are devoted to properties of electrons, and especially focusing on quantum interference phenomena, which are, in some cases, at low temperature, become a prominent properties of metals. The first PhD degree he achieved considering magnetic breakdown in the metals, and coherent magnetic breakdown, when strong enough magnetic field breaks cyclotron motion of electrons and make electronic motion in a plane perpendicular to magnetic field unrestricted in space, and so-called open trajectories. And second habilitation degree was devoted to localization of electron. It's also quantum interference phenomena in a low dimensions, non-linear phenomena, which has to do with localization of electrons. Since 1995, he moved from Soviet Union to Sweden and become a member of our group in Göteborg. And for many, many years, we worked together. And in this period, he was focused on, again, quantum interference phenomena plus electron-electron correlations applied to electric weak link, like junctions, small conductors, and where mesoscopic phenomena become a dominating feature. So, in the very last years, I mean, a new dimension of his activity was connected with nanomechanical degree of freedom in such a weak links, and interplay between electronic and mechanical degrees of freedom. And this was the subject of our activity here in Daejeon, and this is the subject which now will be presented by Leonid.
First of all, I would like to thank IBS invite me to give me a possibility to spend some time in very good surrounding and very productive time. Yes, and I am very glad with it. And especially Robert Schechter and she invite me here. So the topic, as Robert mentioned, now my activity is some combination of electronic and mechanical property. So this is the title, Nanomechanical two-dimensional cat state. We will discuss what is this. Generated by DC voltage driven Cooper paradox. You also consider what it is. This work was done with collaboration with Sergei Kulinich from Kharkov, our previous university Dan Karadzic from Zagreb, and Robert Scheck. Okay, let's start. History and motivation. Actually, motivation was initiated somehow by well-known Stein-Podolsky Rosen paradox. And this is paradox related to the entanglement. When it's in the beginning of quantum mechanics, they argue that quantum mechanics allows so strange state for particles in very big distance, so-called entangled state, that measuring of state of one particle immediately affects the result of measuring of another particle. And then they argue that it's very strange because that action taken on one particle would instantaneously affect, since they would involve information being transferred faster than light. So this was topic. It was very surprising and very counterintuitive. Then approximately at the same time, immediately, Schrödinger also considers this situation and another some counterintuitive aspect of quantum mechanics. It's known as a Schrödinger gap. He suggested some thought experiment, very well known, when this is a radioactive object, which may be in two states. Yeah. And then if in one state, then it's non-active, in another state it crash some poison bottle and kills the cat. And finally, it turns out that we have entanglement in which involve a live and dead cat. And of course, entanglement of decay and not decay cat. So but from this entanglement, Schrödinger argues that how it's possible. Cat is a very big creature. How it can be entanglement? Yeah, and then another question appears: where is the border between classical and quantum mechanics? Of course, I don't want even touch these epistemological questions, but nevertheless, after this alive and dead cat start to live in his own life. It's known as a Schrödinger cat state, but it's not there in entanglement. Let's imagine that this alive cat now repair this guy and bring it in only one state, not in a superposition, but themselves is still to be in two state dead. And okay, and after this, so this state, which dead and alive, start to live its own life. It's known as it. And even now, they're using quantum computing, and it's known as for some so-called bosonic code. Yeah. So this is our topic, and we will consider something like this. Our idea is not to kill the cat, it's not good, but to create two cat state which are quite opposite. So this is not exact definition. What is not a cat state is actually my definition. So this is quantum state that is a superposition of two semi-classical quantum states, which is very close to classical, with opposite classical characteristic. So we are looking for this state, and we will discuss how can we create it. Okay, Nanomechanical to decoherent state. It's best. So for CAT, we have to choose some physical object. Yeah. And among all physical objects, most classical, which can be represented as a quasi-classical behavior, is a quantum oscillator with frequency omega and mass m. So this is the object which we want to discuss. This is actually, it's not two oscillator. I consider this is one oscillator in two dimension, but frequency is coincide. I even don't want to think about what will be not coincide. Yeah, but it needs some symmetry. And this representation is started way, and this is in the Fock space, and then we can create this well-known annihilation operators and introduce some universal quantity A0 divided by m omega, which is actually the characteristic size of wave function in ground state of this oscillator. Okay, next. But this is a mechanical object. Of course, sometimes it's very often. For mechanical oscillator, we can use some electromagnetic fields. But from my point of view, and it's also very interesting, but for me, it's CAT is more mechanical than electromagnetic. So we will consider this one. But we have this quantum evolution, but unfortunately, because of quantum mechanics well known, there's computational relations, which give some restriction for the quantum fluctuations. So there is quantum fluctuation of position and quantum fluctuations of the momentum, and they're always greater with the dimensionals, greater than 1/2. Yeah, so we have to choose, but we want to diminish this quantum fluctuation to be as possible classical state without quantum mechanics. And this is well-known state. This is all coherent state. Informal, this is coherent state, it's eigenstate of this operator. Nothing more. This is mathematical definition, nothing more. And if you can see, like this, multiply, and this is characterized by some complex number. And it's proven that for this state, this guys is minimum 1/2. Okay, but unfortunately, this state doesn't eigenstate of our operator, because A doesn't commute with operator, and it's obvious. So they involve in time. And if we start from really coherent state with very small uncertainty, quantum uncertainty, then maybe after some time, this uncertainty increases and it's true, everything. But it's typically, we can construct this state for any mechanical system with any electron at the beginning. But if it's not the harmonic oscillator, then it's times this uncertainty increase.
Sorry, take one thing.
But if we have coherent state, it's not eigenstate of our operator. It's a second. Eigenstate. It changes in time. But how it changes in time? The modulus of this guy is the same. It doesn't change in time. But phase changes in time proportional to the frequency multiplied by time. So, and all this evolution, they continue to be coherent. So this relation to one. So this is a very good object. From one point of view, this is quantum. From another point of view, it's quite classical because quantum fluctuation minimized. Please.
experimentally, can we make the coherent state nanomechanically? Experimentally, can we realize?
Yes. This is no problem. If we have quantum oscillator and apply periodic force, then your ground state will evolve in a coherent state if you use the rotating wave approximation and so on. So it's possible to generate this state without any quantum state. Simply using the quantum oscillator, and maybe not all time, but for some time it will be coherent with the amplitude and so on. And these values might be quite big, much greater than 1. And what type of coherent state we can observe in 2 dimensions? Of course, it is in 1 dimensional, but 2. So this is the general form. They evolve in time according to omega E. This is an amplitude, but there may be some factor I5 which don't synchronize the motion in X and Y direction. And what we have.
But what's capital A?
The capital name is some real number. This is general form. Huh?
Yeah, it's like if it would be 1-dimensional oscillator, it will be M. Or what? Or it's G. What AX, AY are numbers or what?
The numbers. Yes, numbers.
Okay.
Numbers 5, 6, 7. What more?
Amplitude.
Huh? Yeah, it's characterize the amplitude of oscillation. But actually maybe complex number because it's no complex and big complex, any complex number it's also. But it's important that this doesn't depend on time, this doesn't depend on time, this doesn't depend on time, and only this is time dependent. It changes in time, but there is some obvious conservation. Then what we can calculate in 2-dimensional, we can calculate and present the angular momentum. This is form. And this angular momentum commute with electron because of the rotational speed. Yeah, so it will be integral motion for any coherent state in spite of this, they changes in time. And if we calculate with these guys, it will be HXX models. It's not complex. Let it be real. Let it be real. Multiply by psi-phi divided by this eigenvalue. Yeah, and if X, AX, and AY, sorry, AY. If they are greater than 1, so you can see a moment like much greater than H, so they're very well defined classical, almost classical motion. Okay, let's further. If phi equal to 0, the coherent cell motion like this. And angular momentum equal to 0. If phi equal pi, motion like this, and angular momentum is maximum. Phi equal minus pi 2. We have motion in opposite direction with different angular momentum. And again, if phi equal pi, again we have linear motion with 0 momentum. And all in between, we have something like this. A different phi. So controlling this phi and amplitude, we can control different type of this 2-dimensional motion with different momentum and different trajectory and so on and so on. Our idea to get some superposition of 2 of such, for example, state. Of course, we can speak about any superposition and so on, but this is most interesting for us. So superposition of this state and this state. Superposition of two states which have maximum but opposite angular momentum. Okay, to get superposition, we need some quantum object. Yeah. To create any of them, maybe we don't need, but to create superposition, we need some quantum object. And most quantum, among all quantum objects, is two-level system. This is two-level system with Hilbert space C2. This is eigenvector, which consists of two complex numbers. It may be presented using different bases. And these bases will be important for further. And these bases may be presented as eigenvectors of different Pauli metrics. So we can choose any basis for description. This is our choice. And simply this is the definition that E plus 1 is eigenvector of the sigma 1 and so on. Okay, then there is very useful another representation for the level system. This is so-called Bloch sphere representation. So instead of vector, we can consider density matrix constructed with this vector. It doesn't matter, we have equivalent description of quantum mechanics on in terms of density matrix. It's more general, which include simply description of quantum mechanics in terms of Hilbert space. Okay, so any density matrix, it is Hermitian operator who can be presented, characterized by three parameters. In such form that sigma 1, sigma 2, sigma 3 is Pauli matrix. Then this is definition. And then using this, we can create three-dimensional vector and with m square equal to 1. This is pure state. And then we have very interesting representation for this guy. So every state psi we can represent some point in a Bloch sphere, which is characterized by two angles, theta angle from equally and phi angle. If you look here, we see that immediately even in Hilbert space we also have this representation. Why it's interesting and important? Because, okay, next step. Hamiltonian. Hamiltonian in two-dimensional C2 space is also can be represented by some Hermitian operator, and this is most general form of this Hermitian operator. H1, H2, H3, some parameters. Equation of motion. And then what is interesting is that if we want to describe this motion with respect to how it acts on M, so it looks like vector product. And it looks very similar that you have some motion of magnetic moment in some magnetic field. What is important, if you look at this representation, suppose we have only H3. This is equal to 3, and S of only H3. And in this case, the motion of this point along this sphere will be rotation with constant theta. Yeah, and only phi changes. So it rotates around the three axes. For example, if other situation rotates in another, in general, if the rotation is quite complicated, but you would like to. In our situation, we would consider this level system as a single Cooper pair box. What is a single Cooper pair box? Actually, let's consider superconducting grains, 10 nanometer size or small superconducting. So this is a spectrum, this is a ground state, is condensate, and this is some gap between the ground state and condensate. Actually, the ground state of this system, I will speak only about ground state, is depend on the number of electrons in this guy. If number of electrons is even, they can create all these Cooper pairs and jump to the condensate, and that's it. And suppose, but if the number is odd, we can use, we have one extra electron which doesn't find the pair, them and jump to condensate, and it should be somewhere here above in continuous spectrum, of course, and ground state, but this is with extra energy delta. So this is for one guy, and this is for another. Then we have also, so since we consider small grain, we have electrostatic energy, which is, this is capacitance of our small grain. This is gate, which induces some potential here. And you can see that if we have two extra electrons at, and even if they jump to the condensate, they induce quite big extra energy, extra static energy. Yeah. But this, so we increase energy, but it might be continue to be less than delta. And if we have this relation, we have no very well known situation. This is the situation when we have energy, if this guy equal to 0, by choosing gate voltage. We have neutral and two extra electrons stays the same, but one state with one extra electron only, very high. So we have these two states, only two states, with approximately the same energy. Yeah, and this is neutral state. We could denote like this, charge state like this. Of course, we want to make the superposition of these two states. This and this. Yeah? And this is might be Cooper pair box. But unfortunately, we have the number of electrons conserved. So if we have extra electron, where from we get this extra electron? And if we, for example, we lose this extra electron, where they go? We cannot create actually the superposition. So we need to add something to our system. And this is actually bulk superconductor. So now no question, this two extra electrons may be here and maybe here. Capacitance of bulk superconductor infinity, so we don't have any change of electron. The capacitor will satisfy this relation equal to 0. So if we add here also, so we have this exchange, and now we can create superposition. But this superposition, for example, means actually that neutral grain 0, 1, it means that pair two electrons here. And this is 1, 0, it means that electrons. So we have only two states. And then we can take precision. So this is a very interesting result about the parity effect when you have this relation. When we have the same energy for neutral and one charge state, grain was suggested in this paper. And this superposition was experimentally realized in this work and observed that rarely exists such superposition in such system. So this is put. Now system under the consideration. So we prepare everything. We have this Cooper pair box, this island superconducting, in between two superconductors and on the top of cantilever. If cantilever is moving here like this, it approaches superconducting island to one superconductor. This is two gates. And if it would move, oscillate in y direction, so we approach this Cooper pair box to one gate or to another gate. So now we have some interaction between mechanical and this is two-level system, electronic two-level system presented by. This is something which was done, not exactly the same, of course, but this shows that at least something like this exists. So people works in this direction. So this is cantilever, there's some superconductors. So we have two gates which control motion in y direction and two superconductors and exchange of Cooper pairs, let's say it's Cooper pairs to electron. Jumping back and forth between superconductors. We will consider situation when the charge energy, neutral grain, and a grain with two extra electrons has the same energy. So we using this big gate choose in such way, but this is also resist plus and minus, which actually doesn't use any in the middle any potential, but generates some electrical. That will be.
Yeah. So to realize this Cooper pair box, you need a situation such that only one Cooper pair comes from the bulk superconductor to this box and like that way.
Yeah.
So how does that? How is that realized in experiment? Because I would think if you
No.
bring
But look, you see, in an experiment, small grain or back. Look, this guy. This is neutral and y. If you have two full Cooper pairs, so its energy will be somewhere here.
right.
Yeah, and you don't have this also energy will be somewhere here. So we exclude this situation, and if we choose, and we can very well fix the size of this. With all n greater than the huge energy, blockade energy. So only delta is important. That we have to exclude. This is state with one electron. Because if it will be normal metal, so this guy will be here, and it will be some state with energy much less than this two, and that's it. Okay. This one, and this is, so we have exchange of electron. And then electrical field here. And we will consider the situation when the neutral and charged grain has the same energy. Choose this gate. Okay. So this is reproduce. Now, how we will describe this Cooper pair box? We will use this basis E3. It's eigenvectors of sigma 3 matrices. And this is E3 plus. It's one extra Cooper pair on the island, and E minus is orthogonal non-stochastic constant highest. In this representation, total Hilbert space of this guy is C2 multiplied by L2, this one. And Hamiltonian will consist of three terms as usual. It's H mechanical, I will not repeat it. H Cooper box, which in this situation looks very simple. This is Josephson energy, standard energy superconductor multiplied by cosine phi. Phi is phase difference. And H interaction, which describes situation when we change the position. So we change, first of all, change the potential on the grain, because in this representation, because now charge grain will have one term, this is another term, but if y equal to 0, it's in the middle, no change of potential. In order to change potential, we have to approach here and approach here, this is term. This is describe the tunneling exchange between these guys, and if we approach, move grain a little bit here, this is tunneling exchange increase, and this is decrease, and then it will be some modification with across this time. Then what is important? Oh boy. What is important? The energy scale. So what energy we have? H omega of energy of mechanical vibration. For typical, this mechanical and nanomechanical system is around 1 microelectron. Yeah, 10 to the minus 6. Yeah. Josephson energy, it's related like this. Okay. And if Josephson energy is greater and maybe approximately 10 microelectron volts, something 0.1 Kelvin and something like this. Tunneling length. Since exchange between these two guys due to tunneling, so we have tunneling length approximately 0.1 nanometer. It's typical, otherwise it will be not okay. And A0, this is the amplitude of 0-point oscillation. It's approximately 1 picometer. E is electrical field. If we combine all these guys, we will have this small with this parameter. And if we substitute these values, we will see that this parameter is much less than 1, approximately 10 to the minus 1, 10 to the minus 2, depending on different situation. So
0-point oscillations of what? Of the island?
of island, yes, of mechanical island, yes. So we have to substitute everything. Mass of island, the GDT of this cantilever. Okay. And in reality, it's smaller than 1, and it's very good for us because otherwise we need some small parameter to do something. Otherwise, the problem is unsolved. Okay, then what is the formulation of the problem? What do we want? So this is our guy, H interaction is like this. But then we can control phase and we can control electrical field. No electrical field is very easy to control. We simply apply some signal to this gate electrodes. And to control phase superconducting, we use the IC Josephson effect, applying bias voltage. And difference in phase start evolve in time according to this relation. And beta T, you can see this is some coefficient. Here, if we apply some electrical field. What is interesting, important, that if phi equal 0, for example, and this is equal to 0, H interaction equal to 0, so we have two independent systems, mechanical and this is charge system, electronic system, which doesn't know anything about each other. So this is interaction and appears if we switch on this. And so Suppose we interested in what? Evolution of this system. Our initial state evolved in time. Initial state, we will choose the ground state for mechanical, no interaction, for mechanical, and for electronic subsystem. I remind you that if you take this one, it will be something like superposition in different representations will be illuminated later. Problem. Propose a time protocol for this guy and this guy, such that at an interaction at initially equal to 0, finally after n t time, t peak, this is a period of mechanical rotation, so that after this time, we will have some such superposition. This is no entanglement, this is some state of electronic system, but state of the mechanical system is superposition of two coherent states, quite opposite coherent state. This is one coherent state, and this is another state. So this is our aim, and then we can forget about this guy and say that in two-dimensional we have this. Unfortunately, these two states have the same angular momentum. This is modest step, but we will restrict our consideration today only by this.
Don't swallow the phrases, restrict our consideration to what?
Only to this situation when we can create two quite opposite two-dimensional state, but unfortunately this superposition is in some sense, in big sense, absolutely opposite, but angular momentum is the same.
But they did the same because they both go clockwise.
Yes, yeah, so angular momentum is the same, but the state is absolutely opposite.
So the difference is just some phase factor
Yes,
between these two states.
yes, yes.
But then why you speak about superposition, just multiplying your state by some constant?
No. So this is superposition. They are orthogonal.
No, I would.
No, you
continue.
yeah, you can, okay. This is unfortunately, and then this is.
So may I ask, so in a sense, your cantilever is close at the same moment to the left superconducting to the right.
Yes.
And then they rotate.
Yes, and then this, and all during all rotations, they all time goes to one to another, to one to another, to one stronger than.
Векторная структура в смысле.
And this is a typical cat state.
Sorry, another maybe silly question, but what's the difficulty to have opposite angular momentum states in a superposition?
You
At
see,
least theoretically.
no, you will see that this is not easy, but it's possible. But then we have to find this time protocol. And for what you're saying is that what we want, this time protocol will be more complicated. It's easy. It's not very much presented here. And because this time protocol, what we suggest consists of two steps, which we suggest. This is the general evolution operator, and it consists of two operators, of two different types, of two different operations. One we call growth, stage is from 0 to NT. And then some birth state when we do something also. What we have when we have what we want, we will have. So growth operator like this, we have E2 plus state 0, 0, ground state for mechanical oscillator, and after NT, we will have E2 plus the same, but then we generate, instead of 0, 0, we have this real number, and this is pure complex. This is 5, you remember, 5 divided by 2, so we have something like this. If this guy acts on E2 minus, this eigenstate of sigma 2 is minus, so it also evolve in this state, multiply, but these guys are opposite. Opposite position in X and opposite direction of motion. So this is demands of our operator. Since our initial state, if you remember, is superposition of these two. So if we take initially what we suggested, the superposition, finally we will have superposition of these. So this is the first step. And it's the first step that becomes get growth up. You see, because energy equal to 0, now energy is modulus zeta square, so multiply by omega. So energy increase, this guy start to leave, but unfortunately, if this initial state is not orthogonal of these two operator, so initial state, so it is superposition like we suppose it forms. So these two states continue to be in entanglement with a quantum subsystem. Now we want to burn cat. So we use this operator. And what this is not trivial. What we want, we have these two guy transfer from only one. So we have to suggest some operator acting on this state, rotate this and create this, and acting on this, create also this. It's not trivial. We have to use something. Because if we simply operate with electronic subsystem, but in a unitary way, these vectors, if we want to change, they are orthogonal, and after any action of unitary operator, they continue to be orthogonal. But here, we want it's parallel. So what is the difference between here? And it's important that this guy works with this one, this minus plus I. And this guy is minus. And this minus plus make difference in time evolution, so we have to switch again some interaction. Now which acts back from mechanical system to the two-level system. And then we need this one. The second step is to break the connection between the cat and the quantum actuator. How to do this? No, not how to do this.
What is actuator?
Hmm?
Oh, I just for the first time met this word actuator.
No, I don't. No. Yeah.
Okay.
Like, okay.
Sorry, yeah, maybe maybe this is not step. No, you understand this.
Good word, yes.
Growth steps. So in growth steps, what we suggest, we take the bias voltage equal to the H ohmmeter. This coincide with give them some resonance excitation with omega t, and apply electrical fields with a frequency greater, twice bigger than the frequency of mechanical vibration. Yes, and then we have this total. The later it's very good because you see it's periodic. It's periodic in time. This is so if it's periodic on time, then technical stuff. Omega t, h equal to 1. So Rome, this one is simply product of an operator which acts from 0 to 1, so during for 1 period. Yeah, but now we have to find this one using this terrible thing. I don't want further than this is interaction to pi 0 is t exponent. This is integral. This is interaction representation. Terrible expression, absolutely. But periodic in time. And we take this integral. And what we do, we use now that epsilon is much less than 1. So we are keeping only the leading terms in our approximation exactly epsilon square. So if we do this, we get that this operator can be presented in this form. And this is sigma true operator. Believe me. Not exactly because with accuracy to epsilon square. Of course, and we will forget about this. What is this? Epsilon x y is epsilon is our small parameter multiplied by some numbers, which is of the order of r1. I don't want to present it as a huge combination of some Bessel function and so on. That's some new values when you take these integrals.
But Bessel functions of what?
Huh? But Bessel function is some combination of E, Josephson, eta.
Ah, okay. The parameters.
Those are parameters. Yes. And so finally, if we use this, apply to the ground state, so we will find immediately that it's evolved in time according to what we would plus, because this is sigma. Wait, sorry, this should be true. This is true. So this eigenstate of this operator. Yeah. So if we act on plus, this is every plus, every minus, this is every minus. So this is true. Yeah, but we have something which remains from this is epsilon squared too, but it's multiplied by n. And if you want to be honest, so if n greater than 1 of the epsilon, but less than 1 of the epsilon square, we will have very big these guys greater than 1. So we have very.
What is n? Where is right?
What?
There is no n in the Hamiltonian. What is n? I'm sorry, I didn't get it. It's a number of repetitions.
Yes, yeah. Okay, this is n. Because so that's it. So we get the growth state. Second birth state. Now we want destroy the entanglement and create some pure state between mechanical. It's more complicated. So we, first of all, duration of this second step is only 1 period, 1.5 period. What should we do? First of all, in first step, we take phi equal to pi 2. If you remember, at the beginning of our growth step, phi equal to 0, but now. Then apply constant electrical field. And after half period, we go back to the phi equal to 0. So if we consider Hamiltonian of this step, it looks like this. With accuracy to this small parameter is supposed to be small. Here, instead of operator, we substitute, since we have climbed initially, we have coherent state. We change this operator with class coherent value. And then, what is this? You can see that this guy described in some sense a rotation along the 3 axes. Yeah, very simple. And then he shows these details, so we can easily reconstruct now, since commute with this at any time, any moment of time, it can commute. So we can easily define this guy. And what's happened if we choose in proper way this guy, which is proportional to this electrical field, if we choose. So we will get what we want. Okay, this is very difficult to follow, but the idea is, in the end of growth, we have superposition of 2 states. This one, they are positioned in different points and moving in different directions. But they also have opposite this spin state. If we apply electrical field at this moment of time, initial moment of time, this guy starts to move in the area where potential is positive, and then this guy starts to move to the region where potential is negative. So for these 2 guys, this is magnetic H3 field becomes opposite. And they start to rotate in opposite direction, not in the same direction, but in opposite direction. And after this time, so it looks like it's rotated here, becomes here, this rotates opposite here. But if we choose everything and wait a little bit after this period of time, they become parallel. So we will choose this. If we choose, of course, in the proper way, this is H3, which is. So that's it.
Can you repeat what is red arrow and what is blue arrow?
Red arrow is bias voltage, will control phase difference. Blue area is electrical field, which controls the dependence of electrostatic potential depending on shift in y direction, in y direction. That's it.
But it's something that is in your hands. I mean, you took period of voltage being twice as big as the period of electric field, and that's why you need to rotate twice in blue in order to return to the red. But it's doesn't tell
Wait,
me.
sorry. What doesn't, why is a phase difference between two superconductors. If you remember,
Yeah.
the total Hamiltonian, it contains here also Josephson energy multiplied by cosine phi. I don't want. So I have to cancel this term. I want that operation was only due to this one. In order to this, I have to change very fast. Of course, I have to take into account that it's very fast, not be, we have to compare superconducting gap and blah, 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 but it's possible. So this pulse, it simply changed phi. Before it was 0, now it's phi divided by 2, and this term, which was before.
I have a question. You have a question?
Sorry. This term, which in the final of our, this is cosine phi is equal to 1. And I want to cancel it. So I very quickly change the phase to phi, it disappears. And after this, I start operate only with this one. But now I don't need this high frequency and so.
I have a question.
There is a question.
Yeah, I see, yeah.
So what do you mean by the state epsilon xn here? Is this coherent state?
Yes, yeah, of course. This is excellent.
It's a coherent state, and then basically, if you consider Zx is a coherent state by acting exponential of like I epsilon x and p acts on the 0 state, and you can have this coherent state. But the coherent state usually doesn't count, like it doesn't orthogonal. So how can you choose?
Okay, yes. The coherent state is not orthogonal.
Yeah,
You are right. But at peak, when these guys is greater than 1,
So you're saying that it lasts if n is
yeah,
larger?
of course, this is in all my consideration, I suppose, is a growth state. That I wait so long that this guy is greater than 1. Otherwise, it's continue to be some quantum ground state where it was. Yeah, this guy is much greater than 1, so or Levenko between, of course, it's not 0. Yeah, but exponential is. That's it. Oh, that's it. So conclusion. So we suggest some protocol which look like this, consists of 2 steps and acting on this state, which is pure state, is no mechanical motion in ground state. We transfer to superposition of 2 states, which is actually also pure state, which is product of electronic state by quantum superposition on two-dimensional coherent state, and angular momentum of both state unfortunately equal the same, but much greater than h. So this is like this. I repeat that, of course, initially, and it's done actually, it's possible to get superposition of 2 states like this, but with opposite angular momentum. But for this procedure, unfortunately, I will need 4 steps. And to describe all these 4 steps, among these steps is actually 3 steps like growth step, 3 steps, different but like, and 1 step is like this first step, different but like. So in principle, it's possible.
As in the way you calculate the time dependent, do you need some approximation?
Everything is done in the approximation when this small parameter square multiplied by n is less than 1. Unfortunately.
So basically in this unitary operator, you can have some, when you do the time order of the unitary, of the exponential. Of
Yeah.
You have some using some approximation to get the result, right?
Yeah, no, I simply use this is approximate, yes. At time exponent, I consider only first order in epsilon.
Because
Which is simply integral from 0 to all this time ordering integral, which is proportional epsilon square.
Because like all of the terms in your Hamiltonian, not of them like only with each other. So that means you need to have some approximation to calculate the final result, because if the Hamiltonian have the term doesn't commute, it will use Baker-Campbell-Hausdorff formula, it will generate more term. But I think that you use some absolute approximation, that's the final result.
No, yes, I get a few approximation. First of all, it's an epsilon approximation, and another, in the last step, I change, since I know that this is my final initial state or final state is a coherent state. I change the operator to its classical value. Yes, this is another approximation. Of course, it's not another approximation, but in principle, it's possible. Okay, thank you for your attention.
But I'm sorry. So how you will, suppose you manage to create this, how you will detect this superposition? What should you measure to see that you have?
I don't know. I don't know. This is a measuring problem. Sorry. If I solve this problem, you understand.
More questions? Then we should think there were a number of questions.